start. Good morning, everyone. Happy to see everyone after the spring break and prospective PhD students. Today, we're hosting our weekly startup series for new people who are here. It's an informal weekly event for faculty and staff where students can present their research and faculty can present their research, and you can just get to know each other and get to know what everyone is doing in our department because our department is pretty big. And today our speaker is Dr. Runmin Wang. He's an assistant professor in our department. And before he joined us, he was assistant professor at the Department of Statistics at the Southern Methodist University. He obtained his PhD from the Department of Statistics at University of Illinois at Urbana-Champaign. And his research interests include high-dimensional inference, change point analysis, time series analysis, non-parametric methods, econometrics, sufficient dimension reduction, machine learning, deep learning, and recommendation system. A big variety of interests. Let's welcome Dr. Wang.
But most of the research interests are just bluffing, it's not really something you are a good expert for that. But definitely, I have done something among those variety of research interests for sure. And welcome all the new students here. It's a very special today here, so that makes me a little bit more nervous because I don't really expect that we have so many people here. So and it's very interesting that among all the new students, I have already known some of them from Texas A&M already. So it's really very interesting here today. But let's talk about the thing here. We start a little bit late here. So I try to make everything quick and at high level so that you don't really get boring. And I don't really want to see somebody just sleep here and, it's really bad, because all the, smell from the pizza is really distracting. So you cannot really go sleep here. So today, the title is the high dimensional inference and beyond. It's really a high level title, makes me like a cop's of word, something like that. But really, that's what I have done in the last several years for most of my research. I focus on high dimensional inference, but sometimes you just have some thoughts over that high dimensional thing, and you just want to go something a little bit beyond. So that's why I make a title like that. Okay, so what's the motivation of a high dimensional inference? It's very simple because you just have so many high dimensional data sets nowadays. So the motivation is really from the application side because because of the technology now you have, it's really easy to collect all the data. So for example, I'm listing one thing, so-called the microarray data. That's just some data set that's measures the gene expression. So for example, if you have 100 patients or 10 patients, especially for some rare disease, you really have not a very big population of those patients. Then most of the time you just have like 100 patients or like 500 something, depending on your budget, right? You cannot let the sample size go to infinity because of the budget thing. But the number of genes that you can actually measure for each person is actually huge, right? Sometimes it's 10 to the third, sometimes can be even larger. So it's really a very straightforward application for this something so-called the high dimensional data set. Just because we say it's a large P small n, P means the length of each data set, the length of each data point, and n is the sample size. So when the length of the data is greater than the sample size, then that's what I'm saying is so-called the high dimensional data. Okay, and some possible questions, for example, here for this genomic data is like, say, I want to know which part of the gene is related to the disease. That's very fair, right? So that's something like if you have some patients, you want to find some relationship between your Y and your X. Your Y is just like better, the patient or normal person, and your X would be some gene expression. So that's like a regression thing. And or for example, you have a bunch of patients, you might have a bunch of normal people, and you want to combine the gene set from each population. You want to see whether you have some abnormal thing happening here for the gene expression versus for patients versus normal people. So it's like two sample comparison, right? You have a X and Y, you want to compare their features. So these are actually very traditional problems, especially for low dimension. But now because of this new data set, P is greater than N, then you just somehow you have to reinvent the tools here for high dimensional problems. Definitely, there are some other examples rather than the biological example here. For example, you may have some network time series, like, for example, you study, the friendship on Facebook over the time, right? You have a network, and for the network, for each two nodes, you have an edge between them, and you may have a very large number of edges. So That's another example for high-dimensional data analysis. Or for example, you have something so-called optimal portfolio construction. For example, you have thousands of stocks, you have some future options, even Bitcoin, Dogecoins. You have a lot of things going on here. You want to combine them together and find what's going to be the optimal portfolio to make you rich, right? So that's a high-dimensional problem again. So you see, it's not really something special just because of the advancement of the technology. You just have a large data set nowadays. But we have to do something extra because if you go to the traditional statistical analysis book, always you have assumption saying that your n has to be greater than n. Your n has to be greater than p, even much larger. So most of the time you just treat p as 1 or 10, but you have to let your n go to infinity. So that's the thing. But can we reuse that method for high-dimensional problems? So that's the case. If we can, then really there's no need to develop new methods. But unfortunately, no, okay, because of multiple challenges here. I'm just listing 3 of them, but in fact you have okay, it's fine. But in fact you may have multiple ones. Okay, for example, the first one is just simply the traditional method doesn't work. Okay, you have to have new methodologies. For example, I'm listing several very trivial examples here. What if I want to estimate the L2 norm of the mean vector? Okay, that's L2 norm is like the square root of the sum of squares of the components. Then very straightforward estimator would be the L2 norm of your sample mean. That's the plug-in estimator, right? So when P is fixed, that's somehow the best estimator you can think of, right? X bar is the MLE for mu, and because of the invariance property of MLE, the L2 norm of X bar should be a consistent estimator or MLE of the L2 norm of mu, right? That's the simplest one you can think of. But you definitely know that X bar square is not the unbiased estimator for mu square, right? Because you have a variance term here going on. I don't know whether I have a, oh yeah, I have this. So this one is not an unbiased estimator of this one, right? You can verify the expectation of that is this one multiplied by some factor like that. So it's not unbiased, but the n go to infinity, it becomes to asymptotically unbiased. So again, it's consistent. But for high dimension, it's not. So which means in high dimension case, this one is not really a good estimator for that. Very counterintuitive. Because for high dimension, even for the simplest case, you may have a factor p here. So p may be very large, makes this bias not negligible. So X bar square is not really a good estimator for mu square. Here, the square means L2 norm, right? So this is very counterintuitive. For example, if you have a sample covariance, it's no longer invertible again, then p is greater than n, all right? So for example, I don't know whether you have learned something so-called Hotelling t-squared. It's something like this, right? You have to normalize the thing, right? But this one is no longer invertible. That means the t-square statistic doesn't exist. Well, I mean, I should say Hotelling t-squared because that's the multivariate version of the t statistic, but it does not exist. Or for example, the overfitting, right? You have more predictors than the sample size. Then if you train the model, the training loss would be 0 eventually. But the testing loss, the testing error would be still a big amount. And but remember, the goal is like we try to minimize the testing error instead of the training error. So that's the overfitting issue. So all these kind of things happen for high dimensional statistics, and we have to reinvent methodologies. For example, as simple as that, we have to reinvent some tools to estimate that consistently. That's the basic requirement, right? And when you invent those new methodologies, usually you have to develop some new theory. For example, the traditional CLT doesn't work. We don't really know how the large number the theory, how the law of large number, work in high dimensional case. So we have to reinvent the theoretical tools. Then you develop some new methodologies. And the third one is like you may have some new computational challenges, because originally most of the time your computational complexity would be ON or ON squared or something like that, right? But now P is a factor. So sometimes the computation complexity becomes to this, or even P squared, something like that. So you have to think about both ways. It's not really you can optimize, along the sample side. You have to optimize along the number of the components here. So these are all the challenges. Definitely there are some more, but these are the 3 major challenges that I can think of that you need to handle high dimensional statistics, all right? So let's talk about that one by one. So first of all, definitely you need a new method. And later on, depending on your method, you need to develop new tools, right? So let's see. Yeah, so how to possibly solve this problem, right? As I said, as simple as that, you try to estimate mu. In high dimension, you have to somehow reinvent the method here. So here are some possible solutions. I just for simplicity, I assume that your data ID follows p-dimensional, they are p-dimensional vectors. And I'm trying to do the hypothesis testing to test whether mu equal to 0 or not. That's the simplest hypothesis testing you can think of, right? Even for low dimension. Then how to do this? Simply, you are comparing two vectors. Both of them have growing dimensions, right? It's not really easy because the number of comparisons is going larger and larger, right? You have an infinite number of comparisons if you do component-wise. So the first way is going to do something so-called dimension reduction. You transfer the high dimensional problem to low dimensional problem and use our old method to solve it, right? So this is the first method. Sometimes you find the coefficient matrix A such that you project your mu into the space of A. By doing so, this A mu is an m-dimensional vector, and here m should be fixed. Then this is a low-dimensional statistic, right? And you just apply all the low-dimensional method for this problem, and you are done. But here, this A must be selected very carefully because you have to guarantee that A mu equals to 0 if and only if mu equals to 0, right? Otherwise, it does not make sense. You are testing two different sets of hypotheses, all right? But if you know that mu is very sparse, which means most of the components in mu are 0, then this method is very powerful because although mu is a high dimensional vector, but information contained in mu is actually low dimensional. So you are able to project that to a low dimensional space without any loss. Otherwise, it's a high dimensional vector you project to low dimensional space, definitely you lose some information. But if you know that the information contained is actually intrinsically low, then you can project that without any loss of information. So that's a good thing. But you have to find an A that is very reasonable. Most of the time, it's not really a trivial problem. So if you cannot do that, we may think of the method 2, that is, we test the norm of mu equals to 0 or not. Okay, again, this is like a dimension reduction. You are transferring that comparing two p-dimensional vectors to comparing two numbers, right? But here we are doing the norm thing. We compare the norm of mu equals to 0 or not, because that the norm of mu is 0 if and only if mu is 0, right? So that's the equivalent hypothesis. But now we are comparing two numbers instead of two growing vectors, all right? So some popular choices of the norms can be using, for example, the L infinity norm, which is the maximum norm, or you can use L2 norm, which is like the Euclidean norm. You just take the square root of the sum of squares, okay? They're all popular choices. The good thing for this one is you don't really have to find A. So that's the simplest thing. You don't really have to do an extra problem. So in my class, I always say that if you design your method very easily, then the theoretical proof usually is very difficult. But if you try really, really hard to design a very dedicated method, and usually the proof is very simple. It's just like a 1-line or 2-line proof. So apparently method 2 is very simple, but you can see that the proof is going to be very painful. So that's the trade-off here, okay? So here, to be a little bit more general, that the problem we are studying here is like we try to do an inference to test whether a parameter theta equals to 0 or not. Okay, you can do one sample setting, you can do two sample setting. For two sample setting, it's like you compare theta x versus theta y, just like two sample mean testing, right? But when you transfer that to theta x minus theta y equals to 0, again, it comes back to the one sample testing case, right? So we can always formulate, no matter you have a one sample or two sample case, we can always formulate the problem as a vector theta equals to 0 or not. That's the simplest form of the hypothesis testing you can have. And this theta here, I'm very careful using the notation here. This theta does not need to be a RP in the RP. Okay, it can be any high dimensional parameter you can think of. For example, if theta is a mu, then theta is in RP, right? It's a mean. But what if I'm trying to test some hypothesis related to the sample variance? It's going to be P times P, right? Although we can do that like P times P minus 1 divided by 2 because it's symmetric. You only need to test, the upper triangle or the lower triangle. But again, it's like in the order of P squared. So you can do a lot of things extra, beyond this P, but I'm here using an index that's capital L to denote the set of indices. And the size of this L would be the number of parameters you try to estimate. Okay, so this is the notation. But in any case, if you get lost, you just think of this theta as the mu, as the mean vector. It should hold, okay? So this would be our problem setting here. We have to assume this IID for now because even, for IID, it's a very difficult proof. But later on, maybe you can do temporal dependent data, or you can have spatial data with component-wise dependence. That's another thing. Okay. Yeah, so theta equals to theta x1 here is just, just theta is a quantity that derived from the marginal distribution. Because they are IID, so it doesn't matter if theta x1 or theta x2 or whatever. And here I'm just using an index set. For example, if theta is the variance, then theta is sigma ij from some set L. This L is like I from 1 to n, by to p, times 1 to I to p. So something like it's an index set. I'm just trying to use some mathematical notation to make it more general. But you can easily, bring that down if you have a simple case, say variance or mean, right? If that's a mean, then your capital L will be 1 from 1 to p. It's very straightforward. All right. So here's a little bit literature review, but I don't really want to spend a lot of time to introduce, every paper here. But what I'm trying to say is like, it has a very long history for this high-dimensional statistics already. And you can really see that a lot of low-hanging fruits already, be finished. For example, mean testing, they have L2 method, they have a bunch of method. Covariance testing, those are the low-hanging fruit. For mean testing, it's trivial. What should we do for high-dimensional case? Well, you just do that. And for even about the same set of problems, L infinity-based methods are also developed already. Okay, so you have a bunch of things going on here. But the thing is like, when should we use L2 and when should we use L infinity? And does that really matter? Right? Why there's any difference here? Okay, they're all popular choices. If P is fixed, if maybe you have learned that for fixed dimensional space, all the norms are equivalent. Each one is bounded by another one, so they are all equivalent. But when P goes to infinity, that's a different case because they have different things, they have different behaviors.
I have a question. So are you testing for like the global null versus like it's not equals to 0, or are you doing a screening procedure where you're saying that these are the means that are not equal to 0?
That's a very good question. So if I do a screening procedure, that's more like the first solution. You do dimension reduction. Sure. You find some non-zero ones and you transfer that to low dimensional problem. Here I'm doing this global way. I don't really want to find those non-zero items. So I just directly compare the norm. Yeah, so that's a very good question, actually. This is a global testing. You compare the whole vector versus the zero vectors here. And but here I want to focus on the selection of 2 or P. Which one is better? So it is already convinced and proved in the paper that if you have a sparse vector, that means most of the components in mu or theta are 0, then L infinity norm is the best. Well, think of that, right? You just take the maximum of that. You don't really care about how many zeros, right? But if your vector is weak and dense, saying that every single element is very small, but most of the elements are non-zero, the L2 norm would be better than L infinity norm because you're aggregating every single component. So here is a trivial comparison here. For the first one, this is something so-called weak and dense, right? So weak and dense here. So if you calculate L2 norm, it's going to be 1 no matter what P is. But L infinity norm would be this one, and when P goes to infinity, this one goes to 0. So that means you have almost zero information. And for this case, it's a sparse and a strong alternative, which means you only have 1 and non-zero, but that's large. Then you calculate L2 norm and L infinity norm, you find that they're the same. But that does not mean they are equally good, because when you calculate L2 norm, you have to calculate the sum of squares over all components. You're aggregating the information at the same time you're aggregating the noise. So normally L2-based method is more noisy than the L infinity-based method. So they have the same signal, but L2 norm-based method has a larger noise. So that makes actually L infinity norm method is much better. So that's the thing, okay? So I'm talking about sparse and strong. I'm talking about weak and dense. But what if strong and dense? Everybody can do that, right? Even your granny can solve such a problem by looking at the signal. But looking at the data, you can tell, which one is different. But I'm going to talk about those two. And what if it's sparse and weak? Then nobody can tell such weak signal, right? So only these 2 cases are relevant. Okay. I noticed that I only talk about the 8th page, but we have only 20 minutes left. So maybe I'm gonna speed it up a little bit. But I have already delivered all the key message that I'm trying to say is that for high dimensional problem, you really need the sparsity to choose either L2 or L infinity. For different norm, there are a bunch of methods developed, but the sparsity is unknown usually. Then this is a problem we have to solve. How to solve it? Well, maybe why can't we only use one method? Can we combine them two together? That's the way to go, right? If we can combine them together, then maybe that is powerful against both dense and sparse alternative. And this is something we call the adaptive testing, okay? So this method was first mentioned in this Hurst paper. Actually, one of the co-authors will visit our department on this Friday, Gongjun from UMich. So he proposed, or his team proposed a method here, talking about combining L2 and L infinity, all right? Or different other norms, L2, L4, F6, L8. Combine them together, but they only design a method specifically tailored for mean comparison or covariance comparison. But in our paper here, we are a little bit more ambitious. We want to do that for every parameter that you can think of. Okay, but again, we try to keep the same all good properties that, for example, you have a very nice asymptotic distribution. For example, you have some other nice features that allow you to combine everything together, as an adaptive test. So this is the method we are talking about. So the first difficult is that we are trying to do that for every single parameter. That at least you have to have an estimator for every single parameter, right? So to have a universal way. So how to do that without even knowing the parameter you are trying to estimate? So this is the method we are trying to adapt. That's a really popular and common thing used for low dimensional case. It's so-called the U statistic. Okay, for some of you who are not familiar with U statistic, it's very simple. Just like you think of a simplest estimator for your parameter based on any subsample of your whole data. And then once you have that in your mind, that is something we call the kernel function. You just take the average of all possible such subsamples among your whole sample. And the average is so-called U statistic. Here, U stands for unbiased. So your simple, there's only one requirement for your simple estimator, is unbiasedness. For example, I'm trying to estimate the mean. What's the simplest unbiased estimator you can think of for that mean? Each data point itself, right? That's the simplest estimator you can have. You take the expectation is unbiased. The U statistic is like, hey, I just take the average over all such possible estimators. And that gives you the sample mean. All right, so the sample mean is a U statistic, and it's very easy to find. For example, I'm trying to estimate what's the mean square, what's the mu square. What's the simplest estimator you can think of? Well, if you use only one data, it's not unbiased. You still have to estimate bias term. But if you use two data points, because they are IID, so the expectation is mu squared. So that's the simplest estimator you can think of. Then you take the average over all pairs, that's n chooses 2. Okay, I'm using combination here instead of permutation because this kernel is symmetric. X1, X2 is the same as X2, X1. So you only need to think about the order once. But if this function is not symmetric, you have to do the permutation instead of combination, right? So it's very easy. That's the thing is, if you can think of your H, then you can technically estimate any single parameter you have. And usually finding such H is very easy. You just use a little bit of your statistical intuition, you can find it, okay? U statistics is very good. It's the UML even mentioned. So it's the best unbiased estimator you can think of. At least it can be proved for low dimensional case. When P going to infinity, there's no such proof, but we suspect it's still true, okay? Although just nobody proved that. So this is the idea we are going to use. So remember here, suppose we want to construct some LQ norm-based statistic, okay? So equivalently, we try to estimate theta to the q's power, theta norm to the q's power. Then that's the summation of the q's power of each component, right? That's the LQ norm. Then we just try to estimate the theta L. Again, that's a low dimensional problem. We know how to estimate a single parameter, right? Then we just find the simplest estimator you can think of, that is your H. And here, how to transfer that to theta to the q's power. So here's the magic. We do that just simply q times. Each time we use a different set of observations. Okay, we just multiply the q times and use this product as our big kernel in this case. And it's unbiased. Why? Because of IID. So they have different set of data and they do not have any overlapping. So the expectation of the product is the product of the expectation. It gives you unbiased estimate of theta L. So now you find your kernel function by taking the product. And eventually you take the average and that's that. So again, it's a very universal method that can give you a bias estimator for any parameter you're actually interested in, for any LQ norm that you want to use. All right. Again, it's such easy to construct such method, so the proof is very painful, definitely. So we spent about, I would say, 1 hour to construct this estimator, and we spent about 7 months to show it is actually asymptotically normal. Okay, it is asymptotically normal under certain requirements. For example, you assume that your data are weak cross-sectional dependent, and you have some other moment restrictions. But again, it's asymptotically normal. I'm skipping a lot of details here because I think I want to talk about my second part of the talk really quick. But for now, there are 2 messages I'm trying to deliver. First of all, for every single Q, it's asymptotically normal. So that means it's very easy to use. Second, for multiple Qs, if you construct a statistic for L2, you construct a statistic for L4, they are independent. So that gave us a way to construct adaptive tests. How to do that? We are trying to do in this way. So you don't know it's dense or sparse, right? So for example, I pick L2 and I pick L8. Then for each L2 or L8, you can find the p-value, right? Then I'm picking the smallest p-value as my test statistic. If that was smaller than a threshold, then I reject my null hypothesis. As being said, if one test rejected, we rejected the whole. But here we have to know what is our threshold, but they are independent. So that means those p-values are independent. We know that for a single p-value, that's uniform. So when you talk about the smallest of a bunch of independent p-values, that's simply order statistic. So you know the distribution and you can construct a set alpha test. And this one is our adaptive test statistic.
So, many of these parameters will have to deal with the correlation between the gene and things like that, right? Or covariance measures, things like that. So in these U statistic, is there a way to incorporate the, so 2 genes, they can be correlated when we are not considering the effect of the rest of the genes, but when we are considering the conditional correlation, considering the rest of the genes, they can be not correlated at all. So is there any way in these U statistics to take care of that kind of conditional correlation? Or...
There is a way, but for this method, it does not.
Okay.
Because it considers only marginal distributions.
Yes.
And sometimes to join the distribution, but not conditional join this, but not conditional distribution.
Yeah.
But you can construct some conditional U statistics to incorporate that.
Mm-hmm.
But you have to have a somehow parametric assumption for your problem that you know how to do that in that way. In that sense, it can be done, but this method does not. Okay, we only consider some marginal and some joint things here going on. All right. And this is adaptive testing. There are a lot of questions that I don't have time to answer. For example, how many Qs you should select and what are the Qs you should select, right? There are some questions. Normally, based on some experience, some simulation study, we recommend you only need to pick 2. One would be L2, that's to cover the dense case. And otherwise, like 4 or 6 doesn't really make any difference. And if you go more than that, say you pick 3 Qs or 4 Qs, it doesn't really help a lot. So most of the time, you just need to select 2. And there are some other cases that I need to expand, but I don't really have time. For example, for the normalizing here, these are unknowns. How to estimate that? We certainly have a way to estimate that. So maybe you want to go into the paper, but I don't really have time to go through here. So this is the rough idea. That is, for high-dimensional problems, usually you need sparsity, but that's unknown. So why should we estimate that? We just directly combine the dense and sparse test together. And if we can show they're independent, then we can find a very nice size alpha test. Here are some simulation study, but I don't really want to go through that because everybody knows my simulation is good. Otherwise, why show it, right? So power is high, size is accurate. Okay, good. And so a little bit summary here. I'm just trying to deliver the message that for adaptive test, you combine L2 and L whatever together, and you can cover it. But the very easy question that can be asked: why you do not combine L2 and L infinity? L infinity is the best for sparse. L2 is the best for dense. Why you cannot combine those 2? The answer is very easy because I don't know how. I don't know how to prove the adaptive test for L2 and L infinity. So if any of you know, contact me. Okay, I will pay you to finish that project. But definitely that will be my project for sure, because that's the ideal case. We have run some simulation L2 and L-infinity is the best, but we just don't have a way to show because they use a totally different set of tools to prove. One use the traditional central limit theorem. The other one use something so-called Gaussian approximation developed in recent years, but that is really technical. It's technical, so we don't really know how to do that. And here we have a very strong assumption in their IID. They have a very weak cross-sectional dependence, but later on we want to extend that to dependent data, both temporally and spatially. So that's another thing. So this is all I want to talk about for my first project. I only have several minutes, but I still want to briefly talk about my second one, because that answers a more fundamental question. Why high dimension? So I said, well, high dimensional is different from low dimensional case. But can anybody tell me what's the definition of high dimensional statistic? Is P greater than N is high dimension? Is P smaller than N is low dimension? No one ever thought about that, right? So for example, N is 100, P is 20. Is this low dimension or high dimension? Well, most of people will say, hey, this is low dimension because P is 20, right? It's much smaller than N. It's like you can fit whatever method here. But if I treat P as 0.2 times N, the N go to infinity, both of them go to infinity, right? How do I do a symptotic analysis? What if I say P is 0.002 times N squared? That's even faster than N, right? When I go to infinity, P is even larger, much larger. So which one is high dimension? Which one is low dimension? So that's the thing. No one really think about that. Why we have to have this kind of hassle? So this introduced something so-called dimension agnostic inference. That is, we really don't want to have an inference procedure based on some assumption on P and N. Rather than that, maybe we can find some way to do our inference for whatever P and whatever N. They are unified. So this was this paper talked about. They target on very special case to illustrate this dimension agnostic idea. And because I have done some chain point analysis before, that's the familiar that I'm used to work on. So I'm just trying to develop some dimension agnostic chain point detection here for my own research. But again, just as L2 versus L infinity, even for chain point, you have a set of the low dimensional family and high dimensional family. If all the methods can be used interchangeably, then there's really no way, there's no meaning to develop dimension agnostic inference because they can use both ways interchangeably. But unfortunately not. For example, for some low dimensional method, it's not applicable to high dimension. For example, this matrix is not invertible, right? You cannot use that. And for some high dimensional case, if you use low dimensional method, even that's applicable, you may have significant power loss and vice versa. So that means you cannot really use the wrong method. It will be powerless. There's no power at all. So we have to think a way to get rid of that. For a word of chain point analysis, if you don't really know, here is the illustration. Well, in the previous talk, I really spent one slide or two to explain what is chain point analysis. But later on, I feel like it's really not necessary. I give you a plot, you know what is chain point, right? What's the chain point here? That's some here in the middle, right? Definitely, that's a chain point, right? It tells yourself. So that's the chain point in the middle, right? You can see the mean is changing. What's the second one? That's the chain point in the variance, right? You see the fluctuation is getting larger at some point. And what's the third one? You clearly see there's some chain point over here, right? But how to describe it? It's actually the chain point in distribution. This is normal, and this is Cauchy. So you see you have a very large outlier because Cauchy is heavy tail. But some people ask me, hey, I can see the chain point from the graph. Why you need to develop some algorithms? I say, try the fourth. Tell me what's the chain point? Where is it? There are a lot of chain points actually, but the signal is small. And even when you have high dimension, multiple series together, it's really hard to tell by eyes. So you have to have an algorithm to develop that. So I'm going to use the remaining time to briefly talk about my chain point analysis algorithm for dimension agnostic feature. That's basically saying, I'm doing the simplest way. I'm trying to do a chain point in min, okay? And there are two steps to construct dimension agnostic statistic. Think about how to actually achieve dimension agnostic. You have to get rid of the effect of P, right? Otherwise, there's no way. Sometimes P is large, sometimes P is small. To achieve dimension agnostic, you have to get rid of this P. So this is going back to the dimension reduction idea. That is, I'm trying to make the problem to be one dimension all the time. No matter what is your P, I'm trying to project the data to one dimensional space. By doing so, I'm always dealing with a fixed dimension problem. If I can do so, then this dimension agnostic because there's no P anymore, right? So this is the idea. I have to select that A matrix I mentioned before carefully. And here is how I do that. I split the data into 3 pieces. Now, please ignore this blue part. That's technical. Just think about those 3 black parts. Okay, I split that into 3 pieces. I have to do this way because it's time series data. It's ordered, so I have to do that. I cannot pick all numbers versus even numbers. I cannot even randomly split like training and testing split. I cannot do that because it's time series, so I have to do that sequentially. I split it into 3 pieces because this is the change point problem. The mean for the beginning may not be the same as the mean in the end, right? If you think about the mean, shift. Then I have to split that into 3 pieces. And then I estimate the sample mean for the first and the third. This is the pre-mean. This is the post-mean. I take the difference and I use that as your projection matrix to project your data back there. Okay, I use this difference as the A matrix and I project the data in the middle back to that direction. By doing so, there are 2 good things. First of all, it's 1 dimension, right? The inner product, they are numbers. So you are doing change point analysis for 1 dimensional case. So that means whatever low dimensional method you have, you can apply to this transformed data set. Secondly, if you look at the signal here in the transformed data, it's going to be the L2 norm of the mean change, which is exactly the same signal that you try to identify for your high dimensional or low dimensional case. So we do not have any loss on the signal, but we transfer that from P dimensional case to 1 dimensional case. All right, this is the idea. I don't want to go too deep here. I just want to illustrate this method. And here are some theoretical things here. But for the simulation, I just want to convince you that it's indeed dimension agnostic. For x-axis, that means the logarithm of P. So to the right, that means P is larger. P is larger in this direction. So all the solid dots, all the solid lines, they are our competitors. Actually, that's the old method I developed years ago for tailored for high dimensional statistics. And the solid lines are the solid lines apparently they are better. That's the one for the current method. The dots here, they are tailored for high dimensional statistics. So you see, when P go to infinity, no matter what, our dimension agnostic statistics have the same size, 5% all the time. It's really stable. That means dimension agnostic, right? We use the same set of critical values. No matter what P is, low dimension, high dimension, your size is constant, 5%. But if you compare to these high dimensional statistics, you see the size is not very stable. Okay, there are a lot of technical reasons that I can use to explain, but at least you see they are not stable. Okay, so this is a thing that convinces you that indeed this is dimension agnostic. Okay, in this way, and there's actually a byproduct for our dimension agnostic feature is that for most of the high dimensional method, we may require something so-called weak cross-sectional dependence, as I mentioned before. That means the components in the data should not be strongly correlated. But for our dimensional agnostic statistics, somehow we just get rid of this restriction. It's very interesting. We haven't thought thoroughly why this is true, but it's just true. Okay, you can see that from our theory, and you can see that from the simulation. There's no need to assume a weak cross-sectional dependence. So we are actually not just combining the method for high dimension and low dimension. We are combining high dimension with strong dependence and weak dependence. For the power, again, the solid lines are the newly designed method. We have to admit that you see we have a power loss here. Well, the dot lines, they are size inflated. So definitely they have higher power. But even if we do the size adjusted, we just tune down a little bit, but still we have a size loss, we have a power loss here. We have to admit that. Well, because we do splitting. We only use the middle part to do testing. So essentially we lost a proportion of the data. So definitely we should have a smaller power. But in trade-off that, we don't really need to have a size, inflation or deflation. We have an accurate size. So this is always a trade-off. You cannot get anything for free, right? So we have an accurate size, but the trade-off is we have a slight loss because of this training thing, because we do the sample splitting, and only the middle part is relevant. So there are some other issues we have to develop and discuss, but unfortunately we don't have time right now. So I think I'm gonna go to the conclusion for this one is that the dimension agnostic inference is really feasible for this case, and it's very natural because it's a time series, you can just use the head, you just use the tail, and the splitting is natural. For different people, the splitting is unique. You cannot really have your own randomization to do the splitting. And then here you see it's agnostic to dimensionality, also agnostic to the strength of the cross-sectional dependence. That's a byproduct, which is nice. Some future work that I'm going to try to do, for example, now I'm doing testing, but I don't really know where are the chain points. I only know whether there is or there isn't a chain point. So how to figure out the location of the chain points, the so-called segmentation, this is something I'm interested to do. And then now we do min testing, right? Maybe we can do covariance. Maybe we can do distribution like I just showed in the previous graph, right? And there are a bunch of more going on. So this dimension agnostic project is really new that I'm still trying to find, which going to be the correct direction to go to make it optimized. Certainly, there are a lot of things going on here that is not good. For example, what if the chain point in the beginning or in the end, in the proportion that I used to estimate the mean, then it's not in the middle, then there's going to be a problem, right? Or here, for chain point analysis, usually you have temporal dependent, right? It's time is ordered. So what if you have this dependence? How to deal with this dependence? So there are a lot of things I don't really have time to go through. But indeed, there are a lot of projects that going on here that we try to solve that one by one. This is really new. And for me, this is already the low-hanging fruit. I think in the next, I just recently had as a grant related to this project. So later on, I think this would be the thing that I'm going to work on in the next at least 1 or 2 years to see whether we can find a better way to go instead of just doing this type of split. And, for example, what if there's more than one chain point? Then you only do the tail, you only do the head. You only know the difference between the first mean and the last mean, what's going to be the middle ones. There are a lot of problems that are going on here, and I'm trying to figure out what's going to be the best way to solve all these problems. All right, I think this is all I talk about. I want to talk about it's really high level, I understand. So in case you need more details or you are interested in more details, please let me know. All these 2 papers are available on arXiv. You can just simply search the title here and you will find that paper. And maybe we can discuss later on whatever you need and see whether there's can be any interesting collaborations between us. All right. So thank you very much. Again, welcome all the new students coming here. I hope you enjoy your stay and welcome to Texas A&M. Thank you very much. Sorry, what? Online? Yeah, that's a very nice question. Here I'm doing offline because I need the tail and the head to do the direction, to do the projection. But for online ones, you don't really have your tail, right? Because you're getting longer and longer sequence. So that's a little bit difficult. And there's really no intention to do sample splitting or that sample splitting for online one, because for online chain point, for those of you who don't really know what is online chain point, that means you are observing sequentially arrived data. So just like your credit card fraud detection, you spend $50 on Costco every single day, right? 50, 49, 55. Someday, the bank found that you spend like $5,000 for a TV, then definitely they will freeze your card because there's going to be some fraud, right? You have to prove that, hey, I did that because I got a new home, whatever. But that's sequentially arrived data. You get more and more transactions, but at some point, they detect some abnormal transactions data. So in that case, we usually assume that for an extended long period, there's no chain point at all. Like that's your Euro normal spending, right? We know there's a stage that there's no chain point. So we can safely use that stage to find whatever direction you try to project your data in. There's really no way to do the splitting by yourself because by default, there's a length of transactions, there's no chain point. So that's the reason why we focus on this so-called offline study. That is, you have a complete data record and you just want to figure out where are chain points. But for online, that's very nice because dimension agnostic inference is a still important problem for online inference. But I'm not thinking that using sample splitting would be a good way. I'm not saying the sample splitting is the only way to do dimension agnostic inference. All right, there's definitely some other ways that I haven't thought of. But my conclusion is that for online chain point, maybe the sample splitting is not a good way. But certainly it's very interesting if you can find some dimension agnostic inference for online chain points, right? Definitely. But it's a very nice question. Hi.
In the first part of your work for inference, can you consider the case where potentially you have like a functional response, some infinite dimensional parameter?
Not currently. Now we just consider it's still, well, I shouldn't say it's infinite dimensional space, but it's not in a functional way. It's just you know, P, but P can go to infinity. But it's really interesting because if you extend that to functional data, I think all the L2 method, L infinity method combining together is still feasible, right? But for functional data, based on my knowledge, very limited. I know that sometimes you use, again, there are some L2 normal infinity, but in the integral way, right? And then definitely you can combine them together. I don't really see any difference. The only difference is that for this one, I'm using U statistics, and all the theory are heavily based on U statistics. For functional data, you can still have use statistics to approximate the integral, but I just don't know whether the theory can be extended to that far with no cost at all. Maybe it can, but the cost would be, I don't think the cost would be very small. You may have to redevelop some new tools, but ideally, methodology-wise, I think that's definitely something doable. All right, but for this one, it's discrete in the sense that we only have x1, x2, up to xp. They are discrete, but not in a functional way. But that's definitely a project you can, or maybe we can work out later on if you are interested in that. All right. Yeah.
All right, any more questions? All right, let's thank you again, our speaker.